Okay, first of all, if you heard my last video, you heard me say that 6 choose 2 was 12. I guess I'm tired, it's 15. Anyway, another thing I do need to mention, when I discussed about precision ratio limit, which is the tweakable value that lets us combine nearby numbers into one value, we do not combine numbers that are of opposite signs. So in cases where there are sign differences, we don't do that simply because that could really throw off the whole rhythm of the transform. Anyway, okay. So the next phase is what I call binomial prioritization and nesting. So I've shown you how to identify a binomial that occurs in common between various orthobases, but I haven't told you about how we choose one binomial over another in order to do the substitutions. So the first and most important thing we look at is the population. In how many orthobases does this binomial occur? So for example, I've given you a bunch of binomials here that I found by looking at all my orthobases, and I've told you how often they occur. So this one has population 4. That means it occurs in 4 different orthobases. You know, if there's only, what, 6 orthobasis vectors, I guess that's pretty useful. Whereas this one it only occurs twice, not so useful. So the highest population wins. But occasionally we have a conflict because there are some binomials that have the same population, but they also involve the same term. So this one is 1.2 S2 plus S5. This one is 0.3 S2 plus S4. And they both have population 3, and they both involve S2. Well, this could be a problem because potentially they might occur within the same orthobasis vector. So they're mutually exclusive to some extent. So how do I choose? Well, the way that I've decided to do this is to prioritize whichever ratio is closest to 1. And specifically, I mean here 1.2 or 0.3, the magnitude of which of those is closer to 1. And by the way, if this was minus 1.2, for all intents and purposes, I think of it the same as 1.2. Well, the answer is S7, because 1.2 is a lot closer to 1 than 0.3, in a ratio sense and in an absolute sense. So I'll go with S7. And the reason that we want to keep the ratios as close as possible to 1 is because you don't want the coefficients involved, the constant values involved in your transform, to have a wide dynamic range. Because it's hard to combine small numbers with large numbers using addition. You drop a lot of precision. Now, I might add, there's some experimental evidence that suggests that maybe doing this actually has no net effect. But whatever, it's in the code. At the very worst, it doesn't hurt anything. So that's how we prioritize. And by the way, you know, I don't think I mentioned, I'm talking only about real numbered transforms here. There is a way to extend all of this to complex numbers, or quaternions, 4-dimensional quaternions for that matter, but you have to do the same kind of prioritization. And when you're looking at when you're looking at complex numbers, for instance, you would need to pick the ratio whose magnitude is closest to 1, but the number of numbers with magnitude 1 is infinite in the complex plane. So you need to look at a distance to a circle, and it gets really kind of weird. But it is theoretically possible. And precision ratio limit also works with complex numbers, but instead of having a ratio, really, you have like a ratio neighborhood, if you will, like a ratio circle around a particular value. So it is quite a bit more complicated, but it is possible. Anyway, real value transforms, for now, are supported and do give us a lot of leverage in real-world applications. So how does this work? So as I've shown you before, we just defined an S6, and then these are not the same sample points, by the way. I just redrew something at random. And S7, this is a completely different. So this involves S0 and S1. This involves S2 and S5. S8 also involves S2, but involves S4. Now, so far, not very interesting. But then, all of a sudden, we find that the next most popular thing is actually 3S6 plus S8. So not only is it possible to combine the original sample points in binomials, but you can combine a binomial you've already defined and a sample point, or you can combine 2 binomials together. And in reality, this tends to go on. If you have like 1,000 sample points here, you might have 20,000 different nested binomial definitions. By nested, of course, I mean there are, you take 2 existing binomials or a binomial and sample point, and you make another binomial. And then you multiply it by a scaling factor. And so essentially the transform starts to collapse because you identify a lot of these tree-like structures that occur in various different orthobases, and all you got to do is multiply it by a different constant, which we then put in a data table. Now, this is very processor intensive. It involves a lot of shared memory. It's an iterative process, and so it can take on the order of an hour maybe for a 1,000 sample point transform. But this does actually seem to work quite effectively. In fact, what's interesting, the output of all of this, I had a test case where I'd read a white paper on a particularly esoteric type of transform, and it said, well, if you do this variety of the transform, they'll call it variety A, it takes about 2 times the number of operations as variety B. But if you look at it through human eyes, it appears to take 4 times as many operations, unless you really see this deep trick. And for the life of me, I couldn't see this deep trick, right? So I passed it through Orthohack, and sure enough, Orthohack discovered that the ratio of the total number of adds and multiplies for variety A was approximately just over 2 times the complexity of transform B. I have no idea why, but the white paper said it should be that, and Orthohack seemed to have figured it out. Additionally, what we find, which is very compelling with regards to is this a valid approach, is when the preprocessor is working, it spits out all of the populations that it finds. It says I found 200 different binomials, a population 38, whatever. For the simpler orthobasis transform, I'm thinking especially Fourier, you get these very beautiful numbers that come out. For instance, the 8x8, I have a sample of that in the source code. It comes out 32, 32, 16, 16, something, something. I mean, it's this beautiful, power of 2 cascade that you can see, which, that doesn't prove anything, but to me it's compelling that, okay, the populations of the binomials that we find reflect something about the symmetry of the process itself. So it sounds like, it's a credible kind of optimal transform. If I were to see an optimal transform, I would expect it to look beautiful in that way. So that's kind of compelling. Okay, take a break for a sec, and then next video.